Ok, bonjour. Merci d'être venu. Welcome. Thank you for coming. So, where were we in all this mess? So, what happened is we talked about the Hubbard model and we decided to follow what happens with the electron gas. So, basically we did the Hartree-Fock approximation for the self-energy. And to compute the charge and the spin response function, you see this is the Green's function at 1 plus. So this is like the C dagger or C dagger C. So that's the charge at 0.1. And when we functionally differentiate with respect to phi, gives us the charge at 0.2 here. And if we have the spins, then we get n up minus n down. Otherwise, also the spin and the charge. Now, this delta G delta phi, if we just use this equation, delta G delta phi is related to delta G minus 1 delta phi. And delta G minus 1 delta phi, you see there is this comes from the derivative of the phi. And it means that the coordinates here on these two sides are the same as this one. And on these two sides, they are the same as this one. And then we get the delta sigma delta phi here. So again, the G's are attached to that. And then we have the outside coordinates that are the same as this. And then the phi is there. And then we use the chain rule. And the chain rule, we get delta sigma delta G delta phi. So we get some chi charge and chi spin again here. And then there's a mess dealing with the spins, but in the end, this is what it gives. So another way to look at this is that we put these two legs together, we put these two together. So this is the susceptibility, and then the chi zero is just this, and so there's a minus sign here for the charge, minus. So chi zero is minus G1, G2, G1, I'm sorry, G1, 2, G1, G2, 1. And then we have this irreducible vertex here, and the same that comes here. So we can look at this from if you want, algebraically or with the diagrams. And then we, given the Hartree-Fock approximation for sigma, we can do these functional derivatives, because basically sigma is just this times G and this times G. So we do the functional derivatives and we get to this result for charge and this one for spin. So what happened then is the chi zero was equal to -2. So let me write all the indices. Chi 0, 1, 2 is equal to -2 G1, 2 times G2, 1. And when you take Fourier transform, then this is just susceptibility as a function of Q, and here we will get a convolution. Okay. So the first and the last coordinates here, it has the first coordinate and the last coordinate is here. And then this coordinate is attached to this on either side. And this then is comes from delta sigma delta G delta phi. So this is attached to this. So in the Hartree-Fock approximation, everything remains local, and this then will become minus chi 0. So the plus u that we get here comes from this. And the minus here, the minus u over 2 comes from this, and that's because the only derivative, functional derivative here that's different from zero is the one that comes from here. Why? Because this, remember, we have the Hubbard model, so up spins interact with down, so that's the only thing that was left in the in this approximation. Okay, so that summarizes what we this Hartree-Fock thing. But well, we had problems with Hartree-Fock and RPA. This is RPA. Well, it gave a phase transition in 2 dimensions, which is not allowed. And also you can see from here right away that it violates the Pauli principle to second order in U. So this sum rule here was just a statement that if we sum over all wave vector and all frequencies, we get the equal time quantity. Equal time and same position. And then we use that n up square is equal to n up and down square is equal to n down. That's the Pauli principle. And then you see that when you add these 2 equations, you get something on the right-hand side that's independent of U. But on the left-hand side, if I expand to second order in U, gives something non-zero. So today is how do we fix this? So the approach that will be shown here that satisfies the Mermin-Wagner theorem is the 2 particle self-consistent approach. That's not the only one that does that, satisfies Mermin-Wagner theorem. But for the Pauli principle, that's the only one I know. And okay, so we will proceed just like we did before, in the sense that we will have some approximation for the self-energy, and we will use it to compute the vertices here. And then we get a better approximation for the self-energy. In other words, we will use what we have here for the fluctuations, the charge and spin fluctuations. We will use it here to improve what we have for the self-energy. Very analogous to what we did for the electron gas, huh? Remember? With the electron gas, that's what we did. We just used as a vertex here, we just used this one here. And then we got our RPA here, and then we put it back to get a better approximation for the self-energy. That step I didn't do in much detail, but one way to see this is that if you want, the collective modes, they depend a lot on conservation laws and things like that. Not so much as whether the particles are broad or not. So we will have an approximation for the collective modes here that will be based on expanding in Green's functions that are basically non-interacting Green's functions. But the collective modes have some low frequency components, and the self-energy will be sensitive to these. So that's why we do this in this order. And again, it's the same order as with the electron gas. So that would be the other step. Then I would show you that in this TPSC, there's a sort of an internal accuracy check that we can do. And then I'll show you some benchmarking, in other words, comparing with some exact results. But in this, I will show explicitly that the Mermin-Wagner theorem is satisfied. I will show you another phenomenon that's called Kanamori-Bruckner screening. That's another way of screening, not by long-range forces, and that was found in with nuclear matter first. And then I'll show you the benchmarks for spin and charge and self-energy. And I hope probably won't have time to discuss the pseudo gap in the electron dope superconductors. So that's the plan. Big plan, huh? Is it okay? Okay. So let us first remind ourselves, let's just keep this here. So this here, this combination will be the U charge, because this, I'm missing the minus sign, so that will be minus chi0. And when I resum this algebraic equation, I get it in this form. So this minus becomes plus on the other side. So this is U charge. That's that is U. Okay, sorry, I'm speaking too quickly. And let us first think about how can we fix this Pauli principle business. Suppose that someone gives us an up and down. Okay. Then I could think that here I have a spin, a U associated with spin, and a U associated with charge. And they don't need to be the same, because you see that they are not the same there. Okay. So if someone gives me this, then I can fix the Pauli principle just by, getting the spin and the charge this way. And then U charge will be this. So in principle, there are four indices to this. 1, 2, 3, 4. There should be 4 indices to this. But in the R3-Fock approximation, there are delta functions all over the place, so it becomes local. And this is exactly what we will assume. That's what we assume here. So it's completely local. So you will see how it works out. So now this is minus U spin. So I need to put minus, plus, and that's U spin. So what I will do now is I'm missing one equation, okay, because I have 2 unknowns, U spin, U charge, and a third unknown here, and up and down, and I have just 2 equations. So 3 unknown, 2 equations. We will see. So now I'm going to show you how we manage to get another equation to solve this, and the result will be that U spin is equal to U times N up and down divided by the expectation of N up times N down. So you see that if I can show you this, then I have 3 equations and 3 unknown. Okay, so I have everything I need. There's no adjustable parameter. I can find U spin, U charge, and N up and down. So I'm going to erase this in the peril of my life. I hope. I don't think I need it, but okay. So is it all right here at this point? The plan is clear. I need to show you this. And if I can show you this, then you can find the spin and the charge fluctuation.
Just here. So if you fix N, so the occupation, then you can get chi0 exactly from N, or?
Yes, that's a very good question. Yeah, that's a very good question. So we fix, you see, we work in such a way that when U is equal to 0, this is satisfied exactly. So it means that the N, you just use a Fermi function, basically, and then the chi0 will satisfy this equation. You can check this. Okay. Now I will show you. Let me share my screen.